Hi, my name is Professor Dr. Mehdi Khan, and today I will talk about the radio astronomy, ALMA, Atacama Large Terahertz Array. So I'm a professor at Hunan University currently, and I'm a senior consultant for total artificial hardware design with United Christian Hospital and Peking Indian Medical University. And also I'm a senior consultant for the RFIC MMIC MC design and the nanotechnology, especially for the radio astronomy. Uh, Collaborate with the Observing Robotics and in Chile with the Professor Claudia for Terhertz device design. I'm a CTO for Observing Robotics and where we design biomedical devices and for radio astronomy. And also I'm a patron for the journal to publish papers on topic of medical, electronics and mechanical circuit sports. I'm also a patron for the society where we organize some conferences like the society name is Medical, Electronics and Mechanical Circuit Support. So this is like the contents which I will talk now, and in the current talk, I'll talk about my background. I'll talk about my to apply for the proposal, like band 6 to study the jet structure black hole. I'll talk about the terahertz advantages, the constraints, and the application. I'll talk about the terahertz atmospheric benefit, the window, open. I'll talk about the terahertz sensors, benefits for the radio astrophysicist. I'll talk about the galactic region, which covers this frequency and which is difficult to observe using the optical telescope, and also the benefits. I'll talk about the types of telescopes currently in the market. I'll talk about the radio astronomy, and I'll talk about the interferometry techniques and radio astronomy whole system. I will talk about the why we go for the radio astronomy instead of optical. I'll talk about the ALMA, aperture synthesis, correlations for hardware, and I'll talk about the black hole definition, black hole in the galaxy. I'll talk about the Hawking radiation, Einstein theory of relativity related to black hole. I'll talk about the special relativity, space travel near black hole, observational evidence for black hole, like LIGO, which the Americans did in 2015, I think, and test of general theory of relativity, the approval, like this theory is correct. And then afterwards, I will talk about the Roy-Kerr black hole equation for black hole model for the imaging using in ALMA instead of using the theory of relativity. Also, then afterwards, I will talk about the images which is taken by the ALMA M87. I have some videos so that you can understand clearly, and the VLBI array, how we took it, the technique, and I will talk about the black hole Sgr A as well, and the Coulomb matrix black hole, which is some equation which I will show you, the average imaging, and the clustering and average imaging, the polarization, and in the last we will talk about the conclusion and references. Here we go. This is my background. I was normally working in a Terahertz lab in Chalmers, and this lab was joint lab for the JPL, Jet Propulsion Laboratory, Caltech, and Onsala Space Laboratory, OSL. So my work was to design hardware for the Terahertz devices like coupler, filter, hot electron bolometer, mixers. So I was like working for the ALMA project. So this is my research article. On the left side is about the coupler and H-plane horn antenna at 2.5 terahertz, and the right side is talking about the radio astronomy receivers. And my background, I work as a CTO in a Chinese Silicon Valley for a long time, like 3 to 4 years, and the company name was Hong Kong. That was the 7th largest company, and I was working on the projects like Sgr A, Sgr A, MMIC technology design. Okay, currently I'm working on total artificial hardware design, and I'm working with Professor Chaudhary in Pakistan and Chi Chang in China in Peking Indian Medical University. This is my paper on the left side, and I attend some American College of Cardiology conference and PIC Punjab Institute of Cardiology, and my presentation and abroad about the heart transplant. Here we go. Okay, so now we'll talk about like ALMA extension, VLBI. So if somebody like want to interest, so I can give them the slides. So how can they apply for this project? Normally the deadline one was 31st January, which is passed, but the second deadline is 25th April of 2024. So normally they want to extend this ALMA project, and why they want to extend this thing? Because they want to see the black hole imaging at the event horizon. They want to see the magnetic field near the event horizon. They want to study the accretion disk physics of the black holes, the gravitational field around the black hole physics. These all things they want to study by the extension using the band 6 and band 3. And this one is telling about the ALMA extension. Like also they want to see the jet structure, which is being propagate a very long big jet structure from the black holes. So by extension of band 6 and 3, they want to see these kind of things. Okay, so now I'll talk about the terahertz advantages. So basically terahertz is a strong interaction with, they have a very strong interaction with matters. So in all states they can interact with the matter, propagate inside the matter, and also we can study matter very clearly as compared to other frequencies. It have a very significant penetration in some material. It can go very deeply inside with some dielectric, some matter materials and biomaterials. They can penetrate inside with this frequency, and you can study the material properties. Naturally occurring spectral signatures, and it also have a frequency for femtosecond probing. We can do the frequency probing. It has a very high sensitivity for signal detection. If you know about the super heterodyne receivers, which is multiple division of the down conversion, we have very high noise and also dynamic range. So because of this terahertz, we can have a high dynamic range as compared to other frequency. We will have a aperture advantages over millimeter, and we will have a non-ionized radiation. We will have a low tolerance optics, huge available bandwidth. We have a huge available bandwidth, and we have an untapped potential. Okay, there are some constraints in terahertz, like high material loss. When it penetrates, there is a high losses in metals and dielectric. It has a poor atmospheric transmission. We will have a very small window for the atmospheric transmission at this frequency. It can have a noise background for signal detection, and also resonance except in low pressure. It has a poor contrast, huge spectral ratio, and also it will the constraint have a scale focus at best. We have to do focus at the best point, at one point, and we needed very large aperture required for this thing, and also very expensive. It's called the components making is very expensive. What terahertz provides as compared to radio astronomy, we will have a high dispersion and losses. Okay, terahertz application is like for space currently, like for the astrophysics, to study about the Earth, planet, comets, and asteroids. And also it can be used for the plasma diagnosis in the atmosphere. We can do the gas spectroscopy and quantum physics, gas to detect the gases, and also in the chemistry for nonlinear optics, which is a time domain which was started in 1980s. Also, this is like a window for the terahertz. So here we can see we need a region. This region is 300 to 300 0.303 terahertz band, where we can see we can have there is a gases in the Earth atmosphere absorb electromagnetic radiation for most wavelength. For most wavelength, we can have a radiation very high. The visible light this is the visible light, most radioactivity and some infrared penetrate the atmosphere, can do the penetration. Through atmospheric window, wavelength region of high frequency, and there is a lack of atmospheric window at other wavelength. So that's why the reason placing telescope in this space. So this is the region where they can have penetration easily for this frequency. So this window is very important for the radio astronomy because we have very low absorption, very low attenuation as compared to other. So okay, so we can see the terahertz is very important for the astrophysicist, because if we see from here, this region, this is for the millimeter, from 1 millimeter to 100 micron to 200 millimeter, and this is the terahertz region. And this with this region frequency, or this graph is about spectrum of interstellar dust. We can study about the cosmic background at this temperature. We can study about the dust resonance. So we will also see about dust emission heavy molecules with this frequency, and we can see many things like the materials or oxygen, water, or whatever, the carbon uh, uh, with this region. And this is the image for the optical, and we can see this is terahertz frequency image. And this is very useful for study stellar and galactic constituent and evolution cosmology, to study the dust and gas chemistry, cosmology, background physics. To study the background physics, this frequency is very, very important. It covers this region, if you can see from here. So we can study about different gases, what gas they are, and which is deformed, and plasma, and etc. The galactic emission at terahertz frequency, it is like we can study the very young. This one is for the young star, and this is very old. And you can see from here, this region, from 1 to 1000 micron, it's like 1 millimeter. We can study the old star, about the old star, and the new formation of the star. So here we can see, so we can study of energy of the wavelength and show advantages of terahertz detection for probing the earlier universe. And on the right side, this is the Milky Way, and this is the visible IR optical region. And from this spectrum, we can see half the luminance, and 98% of the photon, 98% of the photon released since the Big Bang fall into this submillimeter region. So this region for the 98%. So it is like, if you don't study terahertz, so that means you're losing 98% information. So this frequency is like spectrum millimeter. Galaxy showing luminant power output versus wavelength. Almost 50% of the power is on the terahertz. This was the paper 2000, and this one is this Herschel. So these are the telescope which is terahertz was made. One is the Herschel Space Telescope, which was made 24 years. It takes 24 years for cost 1.5 billion. And the major task was the cosmic dust, to study star formation, galactic evolution, and cosmology. So 98% of all photons we measure in the universe fall into terahertz region. So on the right side, we can see the planet atomic. So we can detect the water, carbon dioxide, metal, and many other gaseous species by using this frequency. So this is very important. If you forget this region, this frequency, so it means you are 98% far away and cannot see anything about this thing. So now we'll talk about the types of telescope. So we have like optical telescope. I will not talk about this thing. We have ultraviolet and X-ray telescope. We have a space-based astronomy like Hubble, which is on the space. We have infrared telescope. So, and the one which I will talk about is the radio astronomy and interferometric technique using radio astronomy, and the ALMA array. So this is my main topic. So radio astronomy is like radio telescopes. It's for radio telescopes, similar to the optical reflecting telescope. These are more like similar to the optical telescope. The less sensitivity, the prime focus, less sensitivity to imperfection due to longer wavelength can be made very large. So it will make it very large. So radio astronomy, this is the biggest telescope. Largest telescope is like 300 meters dish at Arabic. This is the biggest telescope radio astronomy at Arabic. So radio astronomy, longer wavelength means poor angular resolution. If you have a longer wavelength, that means poor resolution. Advantages of radio astronomy: can observe 24 hours. We can observe it for 24 hours, even there is a rain, cloud, and snow. Don't interfere. Observation can, at an entirely different frequency, get totally different information. Like in 200 gigahertz and 1 terahertz, you will have a totally different information. You will know about the gases and everything with different frequencies, and you will understand this gas is what. Interferometry. So interferometry is a technique. It's like combining information from several widely spread into telescope as given below, and it came from this single dish, become a single dish, and the resolution will be that of dish whose diameter is equal to the largest separation between dishes. So the resolution will be far better if the dish the separation is far away. So this is like we call interferometry. So this is like you can see here, there is two antenna far apart. The interferometry involves combining signal from the two receivers. So there are the two receivers. Point is one. There is a 1 point. Both only 1 point, but there's two receivers. The amount of interference depends on the direction of the signal. The interference. So this is like when there is no phase change. So we will have a constructive, very high amplitude when a wave arrives in steps. When wave is out of phase, then we will have a destructive. So here we can see this is the formula for the interferometry, where d is the diameter of the antenna and lambda is the frequency. Normally it is 0.877 to 1.3 millimeter of the radio ALMA frequency, and this is the resolution angle. So this one which I'm showing you is for the M87 resolution we need, because the size is around 7 micro arc seconds. So that means 2 into 10 to the 9. If you put this thing, so we need this size big dish antenna to see the M87 black hole. So for this thing, we cannot make this thing, so we use a different technique. That means we make a resolution here, 2 into 10 to the minus 9 with this thing, and B is the baseline. That means the difference between these two, the distance between this thing, and then we can achieve this resolution. So interferometry can get radio imaging whose resolution is close to optical, and interferometry can also be done with visible light. It can also be done with a visible light, but it's much more difficult due to shorter wavelength. So here is one example. This is an image show planetary disk surrounded by the star H. This is a star, and there is a protoplanetary disk around him, and we use the ALMA array. So these are the arrays of antenna in ALMA. This is like Earth, and this combine them like making one big dish, and then we get this picture using the interferometry technique. I'll talk about this technique in next slides. So this is like radio astronomy system. Here we can see the radio astronomy, surface astronomy study in frequency. The first detection of radio astronomy from astronomical object was in 1933. So here we can see this is the optical image of the stars, and then we have this parabolic dish antenna, and then we get the spectral image of this thing. And on the right side, you can see this is the optical image source observation, and this is atmospheric, which I will already show you, the region which is open for this frequency, and the antenna collecting the signals from here. We send in signals, we're getting signals, and then get into this thing. This is the back and receiving end, and this is like a terahertz frequency to downconvert to very low frequency baseband signal. Back and amplify and transport signal sent to the spectroscopy. So we get spectrums of this thing, then we get spectrum reconstruction, we make a spectrum, and then we do this signal visualization. So this is more like very radio astronomy system, how this works in ALMA and everywhere. So this is like I'm talking about radio system. So this is like SIS technology. This radio astronomy take the picture. This is the backend structure of the receiver. we have some very horn antenna, circular horn antenna, which have a high beam width, and then it comes to the SIS mixer. The mixer don't convert the signal to the baseband, and then it will amplify, and then after that I have signal processing this thing. This is the cryo system. At this we have a very low temperature like superconductor, so and then we get this thing. And this is the software computer CAD simulation of this structure of the SIS mixer with the IF amplifier. Yeah, this is the SIS mixer, and this is the low pass filter, and this is the clean room picture of the real structure of this SIS mixer, and then you can see how this system works. So this is one more thing, and here we can see at less than 100 gigahertz, the antenna, we use low noise amplifier. But when we go for the 100 gigahertz, more than 100 gigahertz, we cannot make a low noise amplifier on the first, because the problem normal structure we normally have a low noise amplifier before antenna. But because we cannot make these transistor at this frequency, so we use the physics-based mixers like SIS mixer or hot electron bolometer mixers, HEB mixer, which is kind of like this thing, and then we don't convert it to very low frequency, and then we can amplify this thing, and then we can do the signal processing, IF signal processing of that object. And the hot electron bolometer is kind of like this kind of SIS mixer is like just like a Wheatstone bridge. It has two transistors here. This is the resistor here. This is some metal resistance here. When you put some photons here, like some energy comes inside, like this one, this is some energy. So it will increase it become heat. Because this thing, the resistance will increase, and we will generate some current. And that current will vary depend on how many photons we get inside. And this is how we do and then afterwards we do the signal processing of this current. And this is the structure. This is on the left side. This is the whole receiver. This is the horn antenna. The signal comes in, and then it comes with the SIS mixer. Then it goes to the low noise amplifier, and then it will down convert, and then afterwards this signal will go to the computer to do simulation. And this is on the right side. This is a small part. This part SIS mixer. And this is telling what is SIS mixer. Is just the SIS mixer is just a two superconductor material. Between them is an insulator. So this is how we make the SIS mixers in the clean room. And also why we need radio astronomy. On the left side is just like the Milky Way, and on the right side you can see the telescopes, optical telescope. The stunning image taken by the optical instrument like the iconic Hubble telescopes are famous worldwide, but there are many details they cannot see. Radio astronomy reveals part of the invisible sky by detecting radio waves emitted by the wide range of astronomical objects. And radio telescope provide a totally different view of the universe. If you can see from here, these are the dust, which are in optical way we cannot see very clearly. So what we do, because we don't understand what is inside, so we go for the radio astronomy. And here we go. So why we need a radio astronomy? So why? To study the coal dust molecules, where the material is, how much they are, what it is made of, and how it's moving, its temperature and chemistry. This is how we do this thing. On the right hand side, we can see this is like we can with different frequencies. You can these are the different frequencies. We can know about the material properties, like what is this, what is the chemistry of this material, what is dust, what is plasma, what is this made of. With different frequencies we can observe that thing. So which is quite difficult with the optical one. So that's why we move to optical to the radio astronomy. There is some images which I want to clear. So on the left, this is like hydrogen gas released by these young stars. Normally they release too much hydrogen, and that makes us very difficult. What is this region inside? And we can say this is like nebula of Orion, and this is like horse head of Nebulon. And here we can see hydrogen gas released by the side, new star gas. And on the right hand side If we zoom this thing, this part of this thing, this is like a nebula of Orion, and this is the optical image of this one, and this on the right hand side is the infrared image. And then afterwards we go for the, this is the nebula Orion. Here we can see the radio, and then we do the radio study to cold gases. We see gas and dust. If we want to study about these gases around him, so we do the radio astronomy. It's like a very big example on the right hand side. This is a 10 light year away disk of the dust. This is a Debye disk, and this is a small star. So we can study about this dust and gases using the radio astronomy. And
Welcome to the video.
okay, now we talk about the radio astronomy, a brief history. In 1933, as I told you, the American radio engineer Carl Hooter provide it was possible to capture a certain band of electromagnetic radiation coming from the universe, with antennas similar to those used in radio transmission. So in 1937, the Gottlieb Ripper, another American engineer, built the first parabolic radio telescope in order to capture and register radio waves. And in 38, they detect the wave emission of the Milky Way. And this is the history of the ALMA. In 1980, the international scientific community developed an interest in creating a radio telescope that could capture at high resolution, millimetric and submillimetric radio band. In 1995, European Organization Astronomical Research in the Southern Hemisphere, the NRO, and the United States, the National Astronomy, Japanese began to carry out the atmospheric trial, this Atacama Large. For many years, in 1993, observers signaled a corporate agreement. They make agreements, let's make this region. So this is like they chose this in NATO Plateau to make a big region for radio astronomy. So the people who work ALMA represent more than 20 nationals at most, diverse culture, language, and profession. In addition, there are thousands of people from distant university, institute, laboratories, and companies who collaborate to make the world's largest and most powerful radio astronomy telescope. Everyone contributes scientific experience and new design, groundbreaking technologies. So ALMA got operated in 2013, just 10 years back, or maybe 11 years, with 66 antennas full operation. This means a huge leap in astronomy, since ALMA will have a sensitivity and spectral resolution 100 times greater than its predecessing the previous telescope. And with a great telescope that have predicted, ALMA will allow us to see things in the universe which we weren't able to see. Okay, this is the ALMA receiver band. If you can see, they are covering this band 1, 2, 3, 4, 5, 6, and this is the frequency range of band, and this is the noise. This is the frequency. This is wavelength, and these are the countries which are connected, like and they are the receivers which they are using right now, the Hamden SIS, and this is the one they on. Okay, so why they choose Chile? So if you can see from here, this region, this is the Chile region. The Earth atmosphere and water vapor it contains absorb the submillimeter radiation. The problem with the submillimeter is water vaporation. To facilitate operation, this wavelength to be located at the high altitude. So it should be located at the high altitude in a dry place. So this region, if you can see from this graph, water vapor graph, you can say this is very dry region, very good for research for the high altitude for radio astronomy. So ALMA is a set of 66 radio antenna located in North Chile, which detect radiation with wavelength this one, and the antenna mobile, allowing excellent resolution. So ALMA, as I told you, constraint of the array continue until 2013. Once finished, ALMA will be the most powerful radio astronomy. It's finished, and though greatly increased resolution. Why is ALMA so powerful? And this is like I was telling you about this region. Because it is located 5,000 meters above the sea level on the Changtao Plateau in Atacama Desert, the altitude and make it an exceptional site for the astronomy. Minimum amount of water, there is a minimum amount of water, and at the site to provide the transparency needed for the antenna to capture millimetric wave without distortion. So why normally this is, everybody know this picture is everybody know about the Big Bang. So now we also know that warm, cold, and dark matter exist. So this is the dark matter, this is the cosmic microwave background, if you know this image. So we can now know the cold and dark matter exist, that to the measure of the wide range of the wavelength with different wavelength throughout the universe. Even after centuries of astronomical observation, scientists today know little about what is the universe is made of. So ALMA study of cold matter permit the observation of the old planet and galaxies. To study the old planets and galaxies to fail to be detected by optical telescope, allowing us to learn about the early universe. So what we can see in the universe today, so this is like different telescope which I was telling you, like scientific telescope. Scientific technology developed today allows scientists to observe, like we have optical, we have ultraviolet. This is like and we have infrared, observe, study warm. We have like radio telescope that capture radio emission from the warm and cold. And then we have a latest ALMA observing millimeter submeter radio waves as well. So these are the images. We can see this is visible light, this is infrared, this is millimeter ALMA radio and X-rays and X-ray Chandra. What ALMA we can see by observing millimeter metric. ALMA can see the so-called cold universe where planet and galaxy are formed, like it will see for the cold universe. Okay, how does an ALMA antenna work? So most antenna used to in radio astronomy have a reflection surface that is parabolic in shape. Because of its geometric characterization, a parabolic antenna can efficiently capture signals. It can capture signals known as focal point, and the wavelength concentrated at the focal point are channel to band receptor located behind the antenna, so-called front end, where signal are amplified and digitalized to be processed. So a telescope capacity to capture detail depend on two things. Is two things. One, what is the diameter of the collecting surface? The color of the wavelength of the light is captured. The greater the wavelength to be captured, greater the diameter we must need. In order to observe with the sharpness of the human eye, a radio telescope such as ALMA need to be at least 500 times wider than a human eye. The construction of such an enormous center, however, is possible. The scientific community then solved this problem by using a interferometric technique. So this is like a interferometric technique. The surface of the antenna is made up of various panels, and the antenna would still work if one of the panels were missing. It is possible to group together multiple antennas inside a large and define surface area where antenna act as a panel. In this virtual antenna, with very big antenna, when a group of antennas synchronized to observe the same object, and the signal captured by each are then directed simultaneously to the signal focal plane. An image is obtained equivalent to the resolution to the image obtained by the single antenna, equal in diameter to the group of antennas. This ALMA located on the will form a radio interferometry with a maximum diameter of 16. It has a maximum diameter of 16 kilometer. So aperture synthesis. This is very important thing for as I told you, like this kind of like they have so many antenna parabolic, and this is like it acts like a one big dish, very one big with virtual focus point here. So here we can see this aperture synthesis technique by Sir Martin Lyer, a Nobel Prize. He made this thing. He said if we need enough points to synthesize the equivalent large aperture, one pair of telescopes sample at the same time. The n telescope, if you have n telescope, number of sample can be n this form. And then we can have a plane of making use of earth rotation. We can use this earth rotation, like earth is rotation. No, we can feel this thing and recognize by the physics layout of telescope. So this is like this thing he said, and we're using with the earth rotation. This is the black hole, and then we can use a Fourier transform. This is Fourier transform image of this thing. We have a aperture synthesis and Fourier synthesis, and then we can achieve this image by using a aperture synthesis. And this is like if you want to do it to learn about the aperture synthesis, I can give you the software and the links after this lecture, and then you can understand how this works. But on the right side, this is the ET telescope, very big telescope, and this is the Fourier transform of this images captured by these telescopes, which have a aperture synthesis and the Fourier synthesis together, and then we get this image. And this is one example. like you can see from here. It's taking the image, the video, and you can understand how this works. With the earth rotation. Correlation. The last thing which we have when we do the interferometry, so we have two antennas, then we do the correlation as well. So the correlation is like this thing: when you have an IF signal from each receiver look like a noise signal, the part of the waveform is really a signal from the source, and the part perhaps the large part is noise. If both signal and noise look same, how do we tell the difference? The essential point is that source signal will be correlated between the two antennas, while the local generation noise signal will not. This is illustrated with the simulation waveform. Here we can see these are the two noise signals from one antenna, voltage waveform, voltage with the second antenna. Then we do the Fourier transform of this thing. We do the correlation, we multiply integration, and then we get one when this thing. Then a major refine is used to second correlation shift, and we do the second correlation using a sine wave with lambda by 2. So for this thing, the component in this dash box in figure and this thing. So the techniques of interferometry invented by the British astronomer Martin Terry, and this to depend on the resolution. And this is like ALMA has two transport that can move the antenna from diameter requirement for each observation. So the transportation known as OTA and LoRa, we are specially designed to move the heavy antenna ALMA group of antenna, which include 54 major and 12 minor antenna with diameter of 12 and 7 meters, with just requirement of the scientific community. So this is more like ALMA uh, the wavelength images. Each antenna has a front end where band receptor converts wavelength into electrical signal to be sent to the back end, a complex and accurate electronic system where the signal are then digitized and synchronized and sent to wire fiber optic to the central computer unit, which is called correlators. So as I was talking about, this is very big antenna. As I already, this is interferometry technique. Whole antenna become a one big antenna. Then it come to the then it could down convert the signal and make it into digital. When it become a digital, then it go to the correlator, and correlator is more like a integration and multiply, as I explained before, and do the calculation of the images. How can they observe? Each year the scientists compete for observation time by present proposal. Priority with the given the project from the different countries, like 14 they are connected. The ALMA has an exclusive software structure that allows astronomers to do many things, from generating the astronomical project to receive the data. So this is what I want to tell about the summary of the interferometry technique. Normally this is like as one image. This is constructive and this is destructive. The black one is a destructive wave like we have. So these 2 points here we can see there are 2 points. This is for the one antenna point because this is Fourier transform, real and imaginary, how we get 2 points. Then we do the aperture synthesis, like I was talking about the aperture synthesis. This is a 3 antenna. We will have a 6 points. 1, 2, 3, 4, 5, 6. We do the aperture synthesis. We do the calibration before we do the some work. So these 3 antenna. We do the calibration. Afterwards, we do the many point aperture synthesis and Fourier transform. Then when we do the Fourier transform, we get many small dots here. White is the constructive, destructive, constructive, destructive image of the many antennas. Afterward, we do the aperture synthesis and rotation. This is called aperture synthesis plus rotating, earth rotation. And then we can see these points become rotate, and then we get this image. You can see it's not clear yet. Then we go for the aperture synthesis, Fourier synthesis, and rotation, and then we can see very clear. So this is how we make the black hole image. Okay, now we'll talk about the supernova type 1. So supernova is like a wave when the star is going to die. There is a type 1 supernova. This is a graphical illustration. There is a binary system. When it become a white dwarf, then become a white dwarf, then become growing white dwarf, and detonation. The type 2 is a bigger one. It means it has a helium alpha. It also has hydrogen. Normal star fusion. Then it will do the massive star implosion. Then we have a core bound, and then we have a very huge explosion. And this one can make a black hole. With this, because the mass of this star is very huge, then it become a very big black hole with a type 2 supernova normally. So black hole is a mass of the neutron star cannot exceed about 3 solar mass. If a core element is more massive than nothing will stop collapse, and it will become smaller and smaller by denser and denser. Eventually, the gravitational force is so intense that even light cannot escape. Here, the gravitational force is very high. The light cannot escape because of the direction of gravitational force, and become a black hole. The radius at which the escape speed from the black hole uh, equal to the speed of light is called the Schwarzschild. The Earth Schwarzschild radius is about centimeter. The Sun is about 3 kilometer. One of the black hole has collapsed. The Schwarz radius take on another meaning. It is a event horizon. Nothing within this event horizon can escape the black hole. So this is the central engine of the active galaxy. This is the leading theory for the energy source. In an active galactic nuclei, a black hole surrounded by an accretion disk, the strong magnetic field line around the black hole channel particular into jet perpendicular to the magnetic field. So this is like a magnetic field, and we have a jet of high-speed particles. So in an active galactic galaxy, the central black hole may be billions of solar stars. The accretion disk is whole cloud of interstellar gases and dust. They may radiate 10 to 20% of their mass before disappearing. So this is like this pair of images show evidence for the black hole at the center of NG21. The center engine of the center portion of this is like M87 shows a rapid motion and jet characterized of particular characterization of surrounding of the surrounding of a black hole. Here we can see uh, this image here, the intensity of this path, and this one is for this path, and this is the jet. Okay, one might expect the radiation to be mostly X-rays and gamma rays, but apparently it is often reprocessed in the dense cloud around the black hole and remit at long wavelength. So here is one image. Particle will emit synchronized radiation. This is like a synchronized radiation, and we'll have some magnetic field as I showed you before. So at the spiral around the magnetic field, this radiation detect non-stellar. This is we can call detectable non-stellar. So this galaxy is viewed in the radio spectrum, mostly from 21 centimeter radiation. Doppler shift of emission from core show anomalous speed very close to the massive object, a black hole. So here we talk about the black hole masses. The mass of the black hole, center black hole, is well correlated with the mass of the galactic budget. And here we can see the mass of M87 is very high as compared to, you can see the Milky Way. This is the mass, and this is the mass of black hole. Here we can see the mass of black hole, how much it is, and the mass of the Milky Way. This is the mass of NG Cypress A, NG M81. These visible and X-ray images show two supermassive black holes orbiting each other at a distance of about 1 kpc. They are expected to merge into 400 million years. So the quasari we see are very distant, meaning they exist at a long time ago, therefore they may represent at earlier stage in galaxy. The causery in the image are shown with their host galaxy, and many appear to be involved in collision. These are the glowing area, we can call this in causery. So the end of causery approach seemed to have been about 10 billion years ago. All the quasars we have seen are older than others. The black hole powering the quasar do not go away. It is believed that many, if not most, galaxies have a supermassive black hole at their center. So this image shows the black hole. This is like a supermassive black hole here at the quasar, and you can see the figure shows how galaxies may have evolved from early irregular true active galaxies to the normal elliptical and spiral. This is how we can see from here. So here this is the Hawking theorem. One is the no here theorem. This means if you want to know about the black hole, how can you find the black hole? You can see its mass, how much high mass, which is spin, angular spin, angular spin, and with its charge. So only these things we can detect the black hole. And also this is the Hawking radiation. So what Hawking says, black holes aren't so black. They are not so very black. They glow in the sky like a coal in the sky, and they radiate. And so over time they lose energy and mass and ultimately disappear over the hugely. This is by Hawking. And this is the formula by Hawking for the black hole radiation. So it's like it emits radiation. Black hole like emit radiation. This is the formula. So now I'll talk about the general theory of relativity of Einstein. So what it's this is the Einstein formula of the general theory of relativity, where we can say this part, this is the geometry space and the time area, and this one is density, matter, and energy. So what American physicist John Wheeler said, the space-time tells the how matter moves. This is the space-time, and matter tells space-time how to curve. So it means like this is the space-time, and then we have some sun or maybe something. So it make a curvature here. So this curvature let other solar system to move around here. This is what Einstein say how the Earth used to work as compared to normal impact on Earth. And this graph is about the time dilation graph. So normally the time dilation due to gravity is weaker than time dilation due to velocity. The Earth time runs slower from the perspective of the astronaut. The clock on the international space runs slightly faster as compared to on the Earth because of the Einstein theory of relativity is quite strong. Then the Schwarzschild, who tried to prove the Einstein equation, he provided the first exact solution to the Einstein equation of general theory of relativity. And here he used this equation, but here there is a time dilation, and this is the radial length contraction. The only problem with this equation, there is a constraint. What? The constraints with the Einstein theory, there is a black hole, wormhole, dark matter, and singularity. And this equation, when there is a one here, so this becomes infinity. That means time stopped, and there is no singularity. By infinity, we get infinity. So to prove the no singularity, to try to prove Einstein equation, they are quietly right now working on the quantum loop theory. So this is like Einstein theory of relativity. This is a special relativity. The speed of light is the maximum possible speed, and it is always measured to have the same value all observed. So special relativity, there is no absolute frame of reference and no absolute state of rest. Space and time are not independent but are unified as space-time. And this is for the general theory of relativity. It is impossible to tell from within a closed system whether one is in gravitational or acceleration. So this is what I was saying. Matter tend to trap space-time and is going so refined straight line, the path a light beam would take. Black hole occur when the indentation caused by the mass of the hole become infinitely deep. So special relativity in the later 19th century, Michel and Morley did an experimental to measure the variation in the speed of light with respect to the direction of the Earth motion around the Sun. They found no variation. Light always traveled at the same speed. This later become the foundation of special relativity. Taking ta- taking the speed of light to be constant lead to some contradiction effect. Length contraction, time dilation, the relativity of symmetry, and the mass equilibrium. So there are space travel near black hole. The gravitational field of the black hole are unnoticeable outside of the few vast radii. Black hole do not stuck in material any more than an external mass hole. So matter encountering a black hole will experience an enormous tidal force that will both heat it enough to radiate and tear it apart. A probing near the event horizon of the black hole will be seen by observing and experiencing a dramatic redshift as it gets closer, so the time appearing to be going more and more slower. In approaches to the event horizon, this is called gravitational redshift. It is not due to the motion but to the large gravitational field. The probing, however, does not experience any shift. Time would appear normal to any slide. So this is like a photon escape from the vicinity of the black hole will use up a lot of energy. Doing so, it cannot slow down, but its wavelength get longer and longer. So what inside a black hole, no one knows. Of course, present theory predict that the mass collapse until its radius is zero, and definitely infinite. But it is unlikely that it is actually happen until we learn more about what happened in such extreme conditions. The interior of black hole will remain a mystery. So this is like observation evidence of this black hole cannot be observed directly, as the gravitation field will cause light to bend around, so it will bend around. So the observation evidence for the black hole, the bright star has an unseen compare that is a strong X-ray emit called Cygnus X-ray, which through the black hole. The existence of black hole binary pattern from ordinary star can be inferred by the effect of the hole have on the star orbit or by radiation from inflating matter. So Cygnus is a very strong black hole candidate. Its visibility pattern is about 25 solar masses. The system's total mass is about 35 solar masses, so the X-ray source must be about 110 solar masses. Hot gas appear to be flow from the visible star to an unseen. Short time scale variation indicate that the source must be very small. So there are several other black hole candidates similar to those Cygnus. The central of the many galaxy contains supermassive black hole about 1 million solar mass. Recently evidence intermediate mass black hole has been found. These are about 100 to 1000 solar masses. Their origin is not well understood. So this is like more precision test of the defined definition of the starlight by the sun gravity was made during the solar eclipse of 1919. The result agreed with the prediction of the general theory of light. So this is like Einstein predicted that the light should be bent by gravity. Sir Arthur Edding lead an expenditure to photo by the 1990 total eclipse of the sun. The photo revealed star whose light has passed near the sun. Their position showed that the light has been bent exactly as Einstein predicted. So if this is the Earth, this is the sun. So this is the distant starlight bent by the, and then the Earth position at this and Earth see the star. So that means the gravitation bend the light, and we can see the star. So there was one more prediction. Another prediction orbit of Mercury, if you can see, precise due to general relativity near the sun. Again, the measurement agree with this. If you can see, this is the Mercury, and it is revolved like this. Then it bends. This one bends. So here it again prove the general relativity. So there, I will talk about the gravitational wave. These are very low frequency, like 10 to 20 gig, 20 hertz. General relativity predict that orbiting objects should lose energy by emitting gravitational radiation. The amount of energy is tiny, and these waves are very difficult to detect. A neutron star binary system has been observed. Two neutron stars, the orbit of the star are slowing adjust the rate of the prediction. If gravity waves are carrying off this source energy, in September 2015, LIGO first observed gravitational wave from the Mercury of two black holes when they combined them together. So now we talk about the black holes of the ALMA, how they took the picture, because we cannot go for the Einstein theory because it comes in a singularity. So then we use a Roy curve. It does not, it says the single point singularity does not exist. There is a ring singularity. The mass does not on single point but depend on the ring motion. Kerr-Newman black hole with spin equation then used this equation, and this equation was used for the to make a model for the M87 and Sagittarius A model for the ALMA project. So this is like a black hole 87 with making a zoom going down to that point. And then we again reaching that point, and this is how we do the black hole imaging using all antenna, combine them together, make a whole one dish antenna. So this is the black hole and general theory of relativity, how this light curve will do. So here we can see this light is going, this is the curvature here. So when this is a black hole, so the light will bend, so it will make a image like this thing. In the between there is no, so the light bends around this black hole and make an image like this thing, as you can see from this video. So this shows the bending of the photons, and then it make a image. This is a total black hole image. So this is the Event Horizon Telescope consortium at 1.3 millimeter, and then we can see that the black hole size is around 40 micro second, and Sagittarius is 40 also at 40 microseconds with the mass of this thing. So they use the band 6 and band 3 to do the black hole detection with 4 gigabits per second, 1 SPW, 128 megajoule pole, and band 6 was at this frequency to see the black hole image. So this was like ALMA in the middle, the whole and the all other radio astronomy combined together to work to take the image of this black hole and make this graph, which is a Fourier transform image. And you can see, and then we did a Aperture synthesis and spheres Fourier synthesis to get the points by Earth rotating using Aperture synthesis technique. So here we can see, so to take an image, so we break the model. So we use a curl black hole model. We don't use curl black hole reiteration. We don't use Schwarz because there is no spin, but we use a curl Newman spin with charge formula to make a black hole model. So here we can see the imaging approach, how we take the black hole image. This is a video averaging image of the black hole Sagittarius stars using curl model. Curl black hole charge model. Here you get, this is one example. Take the clustering of image. This, and then we do the averaging, and then we get this perfect image, which, and we choose that image. And this is the same approach. This is the peta data image of the black holes taken by the each antenna around the world, and then we combine them together. We do the same thing, the clustering, and then do the averaging. So this is the same thing, how this works. This is one black hole image, hole, divided into 4. One, two, three, 4, and this image. Then we comes in and we choose the best one. And then we get the best image of the black hole Sagittarius, and these are the images of the black hole image, 51 micro arc second for the diameter, using the technique of Kern model and averaging, clustering, and polarization as well. So this is the polarization. So polarization is like for these are the two antennas, if you can see, 1 and 2, and we do the single mode. If we want to do single mode, only we need XX. If we go for dual mode polarization, XX, we need XX and YY, and we're using a stroke one only. But if you want for a full polarization, then we need to do the 4 correlation, XX, YY, and YX, and XY as this thing for informatory polarization to get a very good image of the black hole. If this here we can see with a single and this thing we can get this image. When if we do the full polarization, then we can get this image. So informatory, these are the formulas. This is an ideal wall. This is for the total intensity, and this one the V stroke, and this is for the linear polarization, and for this one is the Q. So this is how we do some calculation, which I will not show here. Do the polarization to get a very good image of body, because there is so much bright light, and then we do some polarization techniques, the factorial polarization, different kind of techniques, which I don't want to explain right now, and then we get a very good image. So these are the, if you want to know and read about this thing, these are the two papers, and I write the where we can download here. These are free access, and you can read about this thing, how they do the imaging and polarization. And the summary, right now I talk about the Terahertz benefits, radio astronomy benefits, ALMA, Einstein theory, Stephen Hawking theory, Royal curve. I talk about the interferometry technique, imaging polarization, black hole, and these are the reference. And thank you very much.